let's see what else we can add to perhaps improve the result and what are the features there. But before that, let me explain a little bit. If you recall, I haven't explained much about exactly what machine learning algorithm we are using to make these predictions last time. Well, there are many kinds of machine learning models. There are shallow and deep ones. The shallow ones are the familiar linear regression. Everybody have probably learned that in college or even maybe in high school these days. And the linear regression, as you know, is a regression technique. It tries to predict the magnitude as well as the sign of the target. The cousin, the close sibling of linear regression in the classification world is the logistic regression, which only predicts two classes, 0 and 1, just like what we have currently built Better Ask Hall to do. Now, both of these kind of regressions are so-called shallow model. It's shallow because it is linear, it's non-hierarchical, and it doesn't work with a lot of features, frankly. So simple models often work best if you have less than, as a rule of thumb, if you have fewer than 10 variables. Maybe even 10 is too many. Let's say if you have 5 variables or fewer, it is probably best to use linear regression or logistic regression. But if you have, let's say, more than 10 variables, then a deeper model would work better because chances are some of these variables will have non-linear interactions, which the linear shallow model won't capture. So, and random forest is the next, that is currently the poster child of a deeper model. It is not as deep as a neural network, and as I have mentioned last time, I have not seen much evidence that neural network actually work in financial prediction. And yet, linear regression definitely is too simple if you have too many variables. So, random forest would seem to be a compromise, and it is in fact the most favored model for data that are outside of speech and image and video processing. If you're not dealing with image or video or speech, neural network is too deep for your application. So that's why we implemented the random forest machine learning algorithm. So what is a random forest? A random forest is an ensemble of classification or regression tree, but for now we're going to focus on classification. But what is a tree? So a tree is a method of selecting features sequentially, one by one. It's sort of a greedy search. Okay, so you pick the very predictor, you go through the algorithm with classification tree is that it goes through all the variables, all the predictors that you have entered, and it tries to pick the most useful predictor first and select that. And it will divide the data into two parts based on that predictor. An example will be, let's say you find that the 10-day moving average is decided to be the most important predictor. Okay, the algorithm will pick it. You don't have to pick it. Let's say 10-day moving average. And it will say, okay, in fact, the rule 10-day moving average greater than 10%. Let's say this is the 10-day moving average of the return, of a certain stock, right? So if it might decide the 10-day moving average of returns of this stock over 10% means that we should buy. Let's say it's a trend. It decided this is a trend following is a good thing for this kind of a penny stock. And if 10-day moving average is less than 10%, we would not buy. We would not hold a position in. Okay, so that would be an example of a variable that you would pick first. And particularly, it doesn't only pick that variable; it also pick a cutoff point. Is it 10% would be the threshold for buying or not? It will pick that for you automatically. Okay, and then after doing that, it separated your samples, your training data, into two subsets. The subset that it decided it should not do anything, and the subset that it has greater than 10% moving average. And then it will repeat this process on each subset Okay, so it will again look through all the predictors to see which variable, which predictor can further define, is most predictive of the outcome for that two subpopulation. Those are called child nodes. The two subsets are called child nodes. And etc. It continues like that. Okay, so every time it breaks up the original population into two, it will repeat the process. And in fact, the original predictor that you pick in the parent node can be reused in the child node. It doesn't say that once you use that predictor, you cannot use it again. You can easily use it again. But when you repeat, use it again, obviously the threshold for cutoff will not be the same, right? If the moving average is over than 10% in the last node, chances are the child node will have a more stringent threshold, like return greater than, let's say, 15%. You will cut the population into two. So how it decide whether which variable to use, which threshold to use, and when it should stop. I mean, obviously, at some point you are left with one sample. If your sequence of conditions are long and stringent enough, sooner or later you might be left with just one data sample in one of the tree branch, and you can't go on and further. But typically, we will stop way before that. We don't want it to have such a long sequence of rules so that you only left with one training sample in one branch. So the criteria for how to pick a predictor is based on the Gini diversity index. In other words, you want to make sure that each of the node, each of the child node are homogeneous, as homogeneous as possible, in terms of their target variable. Okay, homogeneous in terms of the target variable. Why? Well, in the trading context, it's kind of clear, right? So, you want to look at all the, let's say, technical indicators, depending on which indicator will give you always positive return. And if it doesn't satisfy that condition, it will give you 0 or negative return. So obviously, if you can find such a predictor, that would be the best. But typically, no such indicator will make sure that you will be able to be profitable every trade, even in the training set. Maybe in the test set, forget it. But even in the training set, it is hard to find a simple technical indicator that will say that, well, if this condition is satisfied, 100% of your outcome will be profitable and 0% will be losing. That's not possible. So typically you will have, even when you satisfy that, let's say the 10% threshold for moving average, you will still get, 60% or 40% are losses and 60% are gains on one side, and then the reverse on the other side. But the goal is you want to make that two child nodes as homogeneous in itself as possible in terms of the target. One branch should be mostly winning trade, and the other branch would be mostly losing trade. So that's the criteria. It's called that for iterating in the classification tree. It's based on minimizing the so-called Gini diversity index. Why am I telling you this? Do you need to know this? You don't need to know this, because as I said, the system that we built for you have incorporated all of that intricacy for you. But I just want to go behind the screen, go behind the curtain to explain a bit about the algorithm to you as to how we pick variables and how we decide whether to predict this is a winning or losing trade or whatever target that you decide to want to predict. I should show you the tree. So this is like one example of a decision tree. For example, it is based on, let's say, comparing the low of the 2 days yesterday with the low of the day before, and it compares maybe the open of today with the open of 2 days ago. So it depends on any feature that you create, and it will go through all these features and decide on the threshold to pick up your original data into groups of semi-homogeneous subpopulations. Hopefully, by the end of the nodes, these are the real children nooks, grandchildren nooks, you will have a very, very clean prediction of profit or losing trade. And generally, the stopping criteria is that if the number of samples in the channel is too small, or when the decrease in average Gini coefficient is too small, it will stop, right? So if it doesn't, you cannot find any variable that can make the subpopulation more homogeneous, it will stop there. Or if the subpopulation getting too small, that means losing statistical significance, it will also stop.